Today we are starting to talk about our functions again, and we're going to talk about the parent functions and transformations put on those parent functions. So, first off, let's talk about a parent function. Now, you've talked about parent functions in previous classes. Does anyone remember what a parent function is? Nah? It's fairly typical. A parent function is the most basic function inside of a family. Now, there are a chunk of families of functions that we talked about yesterday. Sorry, my zoom on this screen and my zoom on this screen are different. So if I'm ever writing off screen, just let me know. What were the families of functions we talked about yesterday? Linear. Absolute value. Constant. Exponential. Quadratic, and starts with an R. Radical. Or specifically, we talked about the square root function, which is because radical is a family, and then there's like families underneath it. It's got like subfamilies. So, constant was one of the families, and its parent function, its most basic function, is f of x is equal to 1. Do we recall what a constant function's graph looks like? That horizontal line was the constant function. So, the parent function, f of x is equal to 1, happens where? Now, f of x is a fancy way of saying what? Y. So it happens where y is equal to 1. That's the graph of not only a constant function, but specifically the parent function. Happens to be 1 above the x-axis. Linear. Parent function is f of x is equal to x. What did the linear graphs look like? They were diagonal. F of x is equal to x has a y-intercept of 0 and a slope of 1. So it will be the perfect diagonal line for that parent. Now the other two that we're going to focus in on, because we're not going to focus on all 6, we're going to focus in on 4 of them, constant, linear, and the other 2 are going to be the quadratic and the absolute value graphs. The quadratic parent function is f of x is equal to x squared, because quadratic meant it had the exponent of 2. What was the shape of the quadratic parent function? U-shaped. Now this U-shaped graph for a quadratic function will always hit 0, 0 for the parent. It will also hit the coordinate points 1, 1 and negative 1, 1. It is a perfectly symmetrical U that continues to increase upwards and outwards. The last parent function that we're talking about today is the absolute value function. Its parent, being f of x, is equal to the absolute value of x. Do you remember the shape of this one? V-shaped. Similar to the quadratic, the absolute value parent function will hit 0, 0, 1, 1, and negative 1, 1. Now, before we move on from talking about these parent functions, one of the things that we talk about oftentimes when it comes to graphs is we talk about something known as domain and range. Those some familiar words? Do you remember what they are? Domain tells us what we can put into a function. Range tells us what will come out. So, if I think about the constant function. If I focus in on the domain of the constant function, the domain is what I'm allowed to put into the x value. Now, there's an x on the f of x piece, but we already established f of x is essentially a fancy way of writing y. So, parent function, y equals 1. Domain is asking what x values I can plug in. Do you see an x on there anywhere? No, which means it's not limited actually on what we can put in. Because what limits a domain is doing things that we can't do in mathematics. Like you can't divide by what number? 0. You cannot take square roots of what kinds of numbers? Negative numbers. Those are the types of things that limit domains. Since nothing is causing issues here, other than the fact that the x doesn't exist, but it ignores that fact, the domain of a constant function is all real numbers. Now there's a couple of different ways that you can write all real numbers. You can write it out in words, or I get lazy and instead of writing the numbers, I write the octothorpe. The hashtag. It's called an octothorpe. That's its actual name. You can use the all real numbers symbol, which is a double barred R. Just a bar with an additional line there. Or there's the really fancy way that says the x values, because that's our domain variable. This funky looking E, which means exists within, and then the double bar R. Ooh, I did not give myself enough space to talk about range. I'm going to write this a little bit out of order because we typically talk about domain and then range, but for this one I'm going to put it out of order because I ran myself out of room. Range, thankfully, is easy. Range is what can come out of the function. It's what the possible y values of the function would be. If we look at the parent function, f of x equals 1, also known as y is equal to 1, what things could y be? 1. And 1 only. So the range of the constant function is really easy. It's y equals 1. Okay, linear. domain and range, and I won't need near as much space. The only reason I needed as much space on the first one is I was showing you all the different ways to write all real numbers. Okay, domain. It's what can go into the function. It's what can go into the x's. The only things that limit this are math that you cannot do. Now, another way you can figure out the domain and range of a function is look at its graph. X is where on graphs? Up and down or left and right? Left and right. A linear function. Does it go all the way to the left? Does my linear graph go all the way to the left? Does it keep going beyond what I can see? Okay, does it go all the way to the right? Yeah. Including all the way beyond? Are there any gaps going left and right where the graph does not exist? No, because if you look at your linear graph, it says it keeps going this way, which means it exists over here, left and right, left over here. Because we're just looking at left and right. You can either say it takes up that entirety of the height, or you can kind of squash the graph down to a flat line and say, if I look at my axis, yep, it's going to exist, 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 it's going to exist. And you can go on forever. The graph exists everywhere left and right. Everywhere meaning all possible numbers, also known as all real numbers. I don't care which version of all real numbers you write. Most people write this one. Now, range outputs is the up and down of the graph. Does a linear graph go all the way up? Does it go all the way down?
Yes.
Are there any gaps in the middle? Or does it just keep going all the way up and all the way down? Just keeps going. There's no gaps in the middle, meaning it could be anything, also known as all real numbers. Now, if you do the fancy version of all real numbers for range, you have to say y exists within the reals, because range is y values. Quadratics. Domain and range. Domain, x values. In other words, I'm looking left and right. Does a quadratic graph go all the way to the left?
No.
Slowly, it looks like it kind of stops going left, but it actually does keep going left. I understand why if you think it's no, but it actually does keep going to the left. It just kind of slows down how it gets there, but it will continue to go. Does it go all the way to the right? Same story. It looks like it's going to stop, but it's just slowly continuing to go to the right. Are there any gaps in the middle? No, it's fully connected, which means the domain is all real numbers. Range. Now we're looking up and down again. Does my graph go all the way up? Yes, it does. Does the graph go all the way down? No, it stops. It stops going down right here. It hits a point and then goes right back upwards. What is the y value, because we're talking about range, of that coordinate point?
0.
0. Because it's coordinate point 0, 0, we're looking at the second 0. Which means my y's are greater than 0.
Or equal to.
But it is or equal to, because it does actually hit that 0. It hits that point. Any guesses on the domain for absolute value? All real numbers. Because it goes all the way left, all the way right, there's no gaps in the middle. Range goes all the way up, but it doesn't go down. It stops at 0. So y is, and it's greater than or equal to, again, because it does hit that point, 0. Now, I'll be honest with you. We're not going to talk a huge amount about domain and range today, but that's going to be kind of where we're going tomorrow with it. Today, we're focusing more on the transformations that happen. A transformation. It's another word that we would have heard before. But do we remember what it means? It's the changing. And for math, it's the change in either size, position, or orientation. In other words, direction of a graph. There are three main types of transformations that we talk about. A translation, which is where we move it up, down, left, or right. There are reflections. And where we flip the graph over. It's called a line of reflection. And then there's the dilations, which is stretching or shrinking a graph. Yes.
For translation, it moves like up and
Yes,
on
it
the
can.
side of the same like that.
Yes, it can move. Essentially, that's two translations that are happening to it. One to move either up or down, and one to move either left or right. It can also undergo reflections at the same time and dilations at the same time. So, here's where our graphing calculators come into play. You're going to see problems today that ask you to graph a function and its parent. And then to describe the transformation. So, in order to do this, first thing, when I give you an equation, one of the things you're going to have to do is you're going to have to recognize what type of function it is. Is it a constant function? Is it a linear function? Is it a quadratic function? Is it an absolute value function? I'm not going to give you radical or exponential today. That's a future us issue. But you have to figure out what type of function it is to know what its parent is, because I'm not going to tell you what the parent function that goes with it is. I am simply going to give you a function, g of x equals, and then we're going to start with just a basic x minus 4. In which family does this equation belong? Is it constant, linear, quadratic, or absolute value?
Quadratic. Linear.
Linear. Quadratic has x squareds. This one doesn't. So, it's a linear function, which means its parent function is the equation y equals x. So, we are going to graph both of our functions. To do that, first thing we got to do is we have to get into the graphing menu. If you have a TI-83 or a TI-84, you're going to follow my calculator on the right. If you have a Casio, you're following the one, left. Left for TI, right for Casio. Okay, to get to the graphing menu on a TI calculator, click this thing that says y equals. It's directly under the screen. Ta-da, you're in the graphing menu. If you need to get to the graphing menu on a Casio, you have to go all the way back to the main menu. So right here, there's a menu button. And it's going to give you a bunch of different options. One of them will say graph. If you have the fancier Casio, the color Casio calculator like I've got, it's option 5. If you've got one of the little yellow ones, it's option 3, but it should say graph. You can either scroll down and hit enter, or you can hit the number that corresponds. Has everyone gotten to this part of their calculator? It is not, but we will deal with it. You've got an equation in yours, click the exit button. Who did I take this from? Why? Okay. Now, TIs and Casios both have separate issues that could pop up the moment you get into this menu. For the TI, it is the 3 plots that you see on top. The plot 1, plot 2, plot 3. If any of those are turned on, your calculator might yell at you. How can you tell if they're turned on? They're highlighted, like my plot 1 is. You don't want any of them highlighted. If any of them are, use your up arrow to scroll to it and click enter, and it will turn it off. That's really the only issue that tends to pop up with TIs. Occasionally, they don't have Ys here. That's very rare on a TI. It's very common on a Casio. My Casio has Ys here. Some of yours might have X's or T's or a variable of things. This happens when the type of the graph gets changed. So if that, for any reason, is anything other than Y's, click F3, which is the type of graph. We want Y equals graphs. So when type is up, it gives me these options along the bottom, like Y equals. And now they should all be Y's. Now I've got an equation in mind. I don't want that equation. It's got to go away. So I'm going to click delete. Delete. And then do you want to delete it? Yes. And the TIs, I just clear anything that's in there. Okay. I want to put in x minus 4. X on your calculators. On the TIs, it is right here, right next to the colorful alpha button. On the Casios, it is right here, below the colorful alpha button. X minus 4. Click enter or the return bottom corner, and it will get off of that then. We also want to graph the parent function. What's the parent function for linear again? Y equals what?
X.
X. So I also want to put that in here. I'm going to put that as Y2. And I'm going to click enter. From here, you can click graph, and it should, in theory, show you your graph. Note I said in theory. Does anyone have one that doesn't look like that? Sometimes what happens is your graph's window gets changed. And then all of a sudden you have something that doesn't even look remotely close to what we originally had, even though it's the same equation. If you have that happen on a TI calculator, click the zoom button and go down to 6 for a standard zoom. On the Casio, click F3, which is a window button, and F3 for standard. exit to get back out of it on the Casio, and then draw again. If that does not work on yours, call me over. Yours says draw. Casio say draw. Draw. After we get punched in, we have to hit enter. Typically it'll say draw over there. Okay, so we just gotta go back and change the type again. There's your X button. And minus. That's the secondary. X minus, and then the second one should just be X. Yep, F6 is draw. It's angry because you used a negative button instead of a minus sign. So make sure you use this one minus.
This never get done.
Something was done here, so that's why it's.
There we go. Thank you.
I have no earthly idea. I have never seen this calculator before. Type white. And now you can delete those off to get rid of them. Draw. Okay, so we're gonna go to viewing window. We're gonna hit the F3 for standard. Exit back out of the viewing window, so click exit. And now go back to draw again. Draw. For some reason saying you didn't. There's always an X that pops up on the screen itself, and that one's no good. Not too worried about it. Okay, I think everyone's got this graph now, right? Okay. So, now that we got there. Now, my graphs are colored. If yours aren't colored, you just have to pay attention to which one shows up first. Or, which one of these should be the parent function? The one that goes through 0, 0. So the top one. How did this graph change into this graph? What happened to it?
Translated downward.
It went down 4. So, we graphed, and the transformation is it translated technically
We can't see it.
down 4. Well, that's no good. Next one's slightly different. Not a whole lot different, but a little bit different. What's different about these equations? Not exponential, wrong word. Quadratic. So I'm going to change my x's to x squareds. So x squared minus 4. And the parent function is now going to be x squared as well. Squared symbol on the calculators. There's the x squared right here, which just puts a squared on whatever you've got. On the Casios, it's right here. You also could always use the up arrow and 2 to put a power of 2. The one that hits 0, 0 is the original. How does it appear to have changed? Translated, how far in what direction? Again, it went down 4. Which means this minus 4 probably always seems to move it down 4. What if, instead, and this time I'm going to leave it x squared so we don't have to change that piece, I did plus 4. What do you think it's going to do? Up 4 maybe? Change my minus sign to a plus sign. My parent function didn't change. Did it move up 4?
Yes.
Yes. What do you think if I had written plus 6?
Up 6.
Up 6. You'd be correct. What if, instead of adding or subtracting 4 to the very end, I did it right where the x was, which is underneath the squared. In other words, I did this. Any guesses on how that's going to change things? So this time, parenthesis, x minus 4, close parenthesis before I put the squared. Zero, 0, 1 is the original, so how did it change? It moved to the right 4.
How do, it's like not a neutral.
You have to click the enter after you write the equation in. Guesses?
Left 4.
Left. So translations will happen when you're adding or subtracting things. It's just a matter of where. If you add or subtract inside parentheses, that's either left or right. Plus being left, minus being right. And this would work for any of our functions. Absolute value, quadratic, all of them. If you're adding and subtracting to the general function, to what you had to the original parent, it will move it either up or down. What do you think will happen if I put a negative in front of it? upside down? It will.
If you do it properly.
If you do it properly, yes. It flipped upside down. Specifically, it reflects across. Now, to flip from upwards to downwards, the line it's flipping across is the horizontal axis, in other words, the x-axis. Okay, again, I'm going to flip-flop if I do it just to the x or if I do it to the entire function. The first time I did it to the entire function. This time I'm just making the x and making it negative before I square it. What do you think's going to happen there? Did you catch it? It doesn't appear to have changed, but it actually did. The reason it doesn't appear to have changed is because a quadratic graph is perfectly symmetric. It flipped across the y-axis. The part that was here went over here, the part that was here went over there. I'm not going to give you a homework assignment today. We killed too much time. We're still going to keep going for a little bit, but just as an FYI, because I know some of you are probably looking at the time. Just a couple more things we essentially got to explore. What if I put a 2 in front of all of it? And again, I could do this to any of my functions. I'm sticking with x squared just because time. That's one thing that often gets thought of, is that it kind of narrowed out. But it's not a shrink, actually. No. You'd think it would be. But when we're looking at this, when you're doing something to the entire function, you're not looking at its left and right. You're looking at its up and down. And if I take it to get it to go skinnier, I don't push down on it, I pull up. This is a vertical stretch. And it's called by a factor of 2. In other words, it is twice as tall. 2 times as tall. If that's easier for you to understand, you can write it that way too. What do you think is going to happen when I put a 1/2 in? And a 1/2 is just 1 divided by 2. To put it into a calculator. Vertically, it got smushed down, compressed, shrunk. I don't care which word you use. Our book commonly uses shrink or compression, but specifically it's a vertical shrink. And it's a factor 1/2. So key things that we're supposed to get out of this through exploring with our calculator. Talking about your translations. If you take f of x and add a number to it, it's going to go up by that number. Similar to like an x squared plus 1. While if you take f of x and you subtract a number from all of it, it's going to go down by that number.
When I put that in my calculator, it keeps putting parentheses.
So when it does that, we counteract it, right? Oh, come on. Putting parentheses around the 1 divided by 2.
Now if you add into the x, that's when it's going to move left by that number. Oops, why did I write 1? I meant to write a number there. And that's like x plus 1 in parentheses squared. While on the other hand, if you subtract from it, it's going to move to the right. That's going to go off again. Reflections. If you put a negative in front of the function, it's going to reflect across the x-axis. While if you put the negative directly in front of the x, it's going to reflect across the y-axis. And we are almost done. We've got 2 more lines to write and then we're done. The last options that we're talking about today are dilations. Now there's technically 4 types of dilations. We talked about 2 of them today. If you take f of x, the entire function, and multiply it by a number, assuming that number is bigger than 1, that's when you have a vertical stretch. Factor whatever that number is. So like that 2x squared example. But if you multiply that f of x times a number and that number is smaller than 1, specifically between 0 and 1, it is a vertical shrink. Factor also the number. That's enough writing for today. Thank you all for being amazing. I'm still figuring out how we're working with the timing. Please make sure my calculators get put back in their case. Don't forget your phones. If you had one of the calculators that I gave you, one of the fancier ones, please bring those directly to me.